Okay, so think about this challenge. You want a material, right, that's stronger than steel but light, really light like plastic.
Yeah, something that could maybe stop a bullet, but you could also say use it in the human body.
Exactly. And for years, scientists, material scientists, have wrestled with the trade-offs. How do you get that amazing strength without making it brittle?
Or how do you make it high performance and also sustainable? That's a huge one now.
It really is. So today we're doing a deep dive into what looks like a pretty groundbreaking solution to, well, to precisely those problems.
We are. We're looking into the, I think, truly incredible world of self-reinforced composites, specifically the ones made from ultra-high molecular weight polyethylene.
Which is a mouthful, so we'll probably call it UHMWPE.
Yeah, UHMWPE for short. And our guide today is this fascinating scientific paper just published August 19th, 2025. It really digs into how they optimize manufacturing for these materials.
Right. So our mission here is to really unpack what makes these UHMWPE composites special, understand the science, which sounds almost like alchemy, behind making them,
Huh. Kind of feels like it sometimes.
and really show you why they're seen as potential game changers. You know, for tough jobs like ballistic protection, medical implants, aerospace stuff.
Yeah, get ready for some real aha moments, I think. Because what these materials can do is genuinely surprising.
Okay, so let's start right at the beginning. What exactly is a self-reinforced composite?
Good question. So
Yeah.
normally you think of composites maybe like fiberglass, right? Glass fibers mixed in a plastic matrix, different materials.
Right.
But self-reinforced composites, or SRCs, they're different. They use distinct components like fibers in a matrix, sure, but it's all derived from the same basic polymer.
Ah, so it's like reinforcing plastic with itself.
In a way, yes. That's why you also hear terms like single-polymer or monomaterial composites. It's all the same family.
And this isn't just some like clever lab trick. You said there are real advantages, especially sustainability.
Oh, absolutely. Think about recycling. Standard composites. Nightmare. You mix materials, they're hard to separate. You often need intense processes like pyrolysis,
Which is basically burning them, right?
pretty much, or complex chemical baths. But with these SRCs, especially the thermoplastic ones like UHMWPE, you can often just remelt them. Much cleaner, much more circular.
Okay, that's a huge plus. Remelting sounds way better than burning.
Definitely. And another big win is tackling weak spots in normal composites.
Yeah.
Getting two different materials to stick together really well at the interface. That can be tricky.
Yeah, I can imagine. Especially if they don't naturally want to bond.
Exactly. But with these polymeric SRCs, the stress gets transferred through things like hydrogen bonding, but more importantly, through molecular entanglement.
Molecular entanglement. Sounds complex.
It just means the long molecule chains from, say, the fiber surface literally get tangled up like microscopic spaghetti with the chains from the matrix material around them.
Okay, like tiny knots holding everything together.
Precisely. And it creates a super strong internal bond. The paper actually quantifies this. It measures the interfacial shear strength, basically how well the layers stick between UHMWPE fibers and a polyethylene matrix.
And what did they find?
An impressive 8.3 megapascals, MP, which might not sound huge, but compared to putting UHMWPE fibers in a standard epoxy matrix that only gets about 1.7 MPa.
Wow, so more than 4 times stronger just by using the same family of material.
Exactly. It shows how efficient this single polymer approach is. The material just bonds better with itself.
Okay, that makes sense. So why UHMWP specifically? What makes it the star here?
Well, UHMWPE, when you draw it into fibers, has this exceptional specific strength.
Specific strength, has strength for its weight.
Exactly. Strength to weight ratio.
Yeah.
And UHMWPE fibers basically give you the best mechanical performance you can get from any polymer-based SRC.
So super strong, but also lightweight.
That's the magic combo. And it's what makes these materials so promising for those demanding applications. We've mentioned body armor, medical devices, lightweight parts for planes or spacecraft.
Okay, so we know what they are and why UHMWPE is special. Now, how on earth do you actually make them? The paper talks about thermal pressing.
Right, thermal pressing. This is where the real careful engineering comes in. They start with these gel-spun UHMWPE fibers. The paper uses a commercial type called Dynemi SK75.
And these fibers are already super strong on their own.
Oh yeah, think several times stronger than steel, but way lighter. So they take these continuous filaments and wind them very precisely into what they call unidirectional preforms.
Unidirectional meaning all the fibers point the same way.
Exactly. Perfect alignment is absolutely critical for getting that maximum strength along the fiber direction.
Okay, got the aligned fibers, then the heat and pressure.
Yep, they put these preforms into a mold, and they apply pressure first, either 25 or 50 megapascals, so quite a bit of pressure before heating. Then comes the really precise heating cycle.
How precise are we talking?
They heat it up to a target temperature, somewhere between 145 and 180 degrees Celsius, over about 50 minutes. Then they hold it at that exact temperature for 10 minutes.
Wow, okay. Baking something incredibly sensitive. Every degree matters.
It really does. Because that temperature window is super narrow. The goal is to slightly melt just the surface of the fibers.
Just the surface.
Right, enough to get them to fuse together, but you absolutely have to preserve the strong crystalline core of the fibers. That's where the strength comes from.
Ah, okay. Don't melt the good stuff.
Exactly. You also want to avoid forming other weird structures, like transcrystalline layers, which can be weak points, and minimize leftover stresses.
Yeah.
After that 10-minute hold, they cool it down slowly, still under pressure, back to about 40 Celsius.
It really sounds like a balancing act. Get enough melting for bonding, but not too much.
That's precisely the challenge. It's a very fine line.
So what did the researchers see when they looked closely at the result? They used electron microscopy, right? SECM.
They did, and they saw something really interesting about the fiber shape within the composite. The individual fibers weren't round anymore. They deformed into a sort of hexagonal shape.
Hexagonal. Why is that significant?
Well, hexagons pack together really efficiently, right? Think honeycombs. This dense packing maximizes the contact area between the fibers.
Which helps them bond better.
Exactly. It enhances that interfacial bonding through what they call macromolecular interdiffusion, which is basically our fancy term for those molecular chains tangling up across the fiber boundaries. More contact means more tangling.
Okay, so the shape helps the bonding, but you mentioned stresses earlier. The paper says this pressing generates internal stresses, and they're like a double-edged sword.
Precisely. On the one hand, these leftover or residual stresses can actually be good. They push the fibers together, increasing that contact pressure, which helps transfer load efficiently when you pull or bend the material.
Makes it stronger, basically.
Up to a point, yes. And the results support this. They found peak strengths, like 11.1 MPa for shear and 130 MPa for bending at those optimal mid-range temperatures around 165, 170 degrees C.
But the other edge of the sword.
If the stresses get too high or aren't managed well, they can create tiny internal voids or defects. And those little voids act like starting points for cracks. They concentrate stress and can make the material fail sooner. So again, it's a balance.
Finding that sweet spot temperature is absolutely key then.
Critical.
So let's dig deeper into that bonding. What's physically happening at the interface? You mentioned tangling chains, but what did the microscope show on failed samples?
Yeah, this was interesting. When they looked at samples that had been pulled apart, delaminated, they saw these tiny hair-like structures called fibrils pulled out along the fiber surfaces.
Fibrils, like tiny threads bridging the gap.
Exactly. And these fibrillar bridges got denser, more numerous, when the material was made at higher temperatures. This is really characteristic of how fiber-forming polymers like UHMWPE fracture when they're well bonded.
So it's visual proof of that molecular tangling.
It's a strong evidence, yeah. It confirms that the bonding happens through that interdiffusion. Higher temperatures mean more melting on the surface. The chains can move around more, penetrate deeper into the neighboring fiber's surface layer, and tangle more effectively. It really is like a molecular dance.
A carefully choreographed dance, it sounds like. Okay, so this whole process, this dance, dictates the final properties. Let's walk through them. First, that interlayer shear strength, how well the layers resist sliding past each other.
Right, so as you'd expect from better bonding, the shear strength went up consistently with the processing temperature, at least initially.
What were the numbers like?
At the low end, 145 Celsius, it was about 7.8 MPa. It climbed quite nicely to a peak of 11.1 MPa, around 165 and 170 Celsius.
Okay, so hotter means stickier up to a point. What happened at the very top end, 180 degrees?
Ah, see, there things changed. At 180 C, the samples didn't really fail by shearing apart cleanly anymore. They just sort of deformed plastically like a solid block of polymer. They lost that layered behavior.
Meaning the heat was too much.
Exactly. It suggests that at 180 C, you've basically melted too much of the oriented fiber structure. It's losing its reinforcement ability and becoming more like a uniform isotropic material.
Got it. Too hot, and you ruin the magic. What about bending? How did it hold up when bent?
Bending strength and also the stiffness or elastic modulus in bending showed a really interesting pattern. It wasn't linear.
How so?
They both increased with temperature at first, hit a peak value, and then dropped off quite sharply at the higher temperatures.
Similar peak temperature range.
Pretty much, yeah.
Yeah.
Maximum bending strength was around 130 MP, and the maximum stiffness around 42 gigapascals GPa.
Yeah.
Again, happening in that 165, 170 C sweet spot for the lower pressure.
And did the pressure they used during manufacturing make a difference here? They tested 25 and 50 MPa, right?
It did make a difference, but maybe not how you'd expect. The higher pressure, 50 MPa, didn't really change the maximum strength or stiffness they could achieve. Those peak values stayed about the same.
So what did the higher pressure do?
It shifted the temperature at which those peaks occurred. With higher pressure, you needed a slightly higher temperature to get the best results.
Why would that happen?
It's related to thermodynamics, actually. There's something called the Clausius-Clapeyron equation, which basically describes how pressure affects melting points. Higher pressure makes it slightly harder for the material to melt, so you need a bit more heat to reach that optimal surface melting point.
Okay, so pressure tunes the temperature window, but doesn't fundamentally change the material's potential peak performance. It's all about hitting that thermal sweet spot.
That's exactly right. And it makes sense when you think about those competing factors we discussed.
Right, the balance again.
Yeah. At first, more heat gives you better matrix development, better fiber matrix bonding, better stress transfer. That makes it stronger and stiffer.
But
then, you keep heating, you melt too much of the fiber core, you reduce the amount of reinforcement carrying the load, and eventually the properties just collapse.
yeah,
It's this constant tug of war.
that really illustrates the challenge clearly. Okay, next property. Impact resistance. How does this stuff handle a sudden hit? Does it shatter?
This was really interesting. They used Charpy impact tests, which involve hitting a sample with a swinging pendulum. And the key finding was none of the samples actually broke completely.
None. What happened then?
They all just bent. They underwent plastic deformation, a permanent bend at the impact site. But the fibers themselves didn't fracture.
So they absorbed the energy by bending, not shattering. That sounds ductile.
Exactly. It's a ductile response, which is a huge contrast to, say, traditional composites made with UHMWPE fibers in a brittle epoxy matrix. Those tend to shatter.
And did the impact resistance change with temperature?
It did. It got progressively better as the processing temperature increased up to that optimal range again. It went from about 72 kilojoules per square meter at 145 C up to around 95 kilojoules at 165 C.
So better bonding helps it absorb impact energy better too.
It seems so. The thinking is that the energy gets absorbed mostly through the plastic deformation of that partially melted matrix material and maybe some controlled slipping or debonding at the interfaces rather than just snapping the strong fibers.
It's like the whole structure works together to absorb the blow.
Precisely. The matrix and the reinforcement are made of the same stuff, so they deform in similar ways. It allows for this efficient energy dissipation through plasticity. It's a synergistic effect.
That's a huge advantage for things like armor, obviously. You want the material to absorb the hit, not just break.
Absolutely. Ductility is key there.
Okay, finally the big one. Tensile strength. Pulling it straight apart. This is where UHMWPE fibers really shine, right?
Yeah.
What kind of numbers did they achieve?
This is where it gets really impressive. Under those optimal conditions, 165 degrees Celsius, 25 MPa pressure, they measured a tensile strength of 1440 MPa.
1,440 megapascals. How does that compare to, well, anything?
It's roughly in the ballpark of some high-strength steels. But, and this is crucial, it's at a tiny fraction of the weight. And the stiffness, the tensile modulus, was also high, around 40 GPa.
Wow. And how much of the original fiber strength does that represent?
That's maybe the most impressive part. That 1440 MPa value represents something like 35 to 50% of the strength of the pristine individual UHMWPE fibers they started with.
35 to 50%. That sounds incredibly efficient.
It is remarkable. It shows that the stress is being transferred from the matrix to those strong fibers very, very effectively within the composite structure.
Okay, 1440 MPa is genuinely game-changing for lightweight strength. But the paper notes something interesting, like high tensile strength? Yes. But the bending strength wasn't quite as proportionally high. Why? The difference?
Yeah, that's inherent to how these aligned fiber composites work. When you pull it in tension, straight along the fiber direction, those continuous, super strong, highly oriented fibers take almost all the load. That's why the tensile strength is so fantastic.
That makes sense.
But bending is more complicated. When you bend something, one side goes into tension and the other side goes into compression.
Right.
The fibers are great in tension, But the compressive strength of composites like this is usually limited by other factors, like the fibers potentially buckling, or the strength of the matrix material between them, especially under shear stress.
Ah, so the matrix part, the bit that melted and fused, isn't as strong in compression as the fibers are in tension.
Exactly. That partially melted matrix is more isotropic, less perfectly crystalline. Its compressive strength just can't match the incredible tensile strength of the oriented fiber core. So the material gives way sooner under bending loads, which involve compression, than it does under pure tension.
Okay, that explains the difference. Strong when pulled, less strong relatively when bent or compressed.
Precisely. It's a characteristic of this type of structure.
Right, so let's try and tie all this together. If you had to point to the single central insight from this deep dive, what would it be?
I think it really comes down to that intricate balance, that constant interplay between competing effects during manufacturing.
The double-edged sword again.
Exactly. You
Yeah.
increase the temperature, and yes, you enhance that crucial interfacial bonding through molecular entanglement that's good,
Mm.
but push it just a bit too far, and you simultaneously start reducing the amount of that highly oriented fiber core, your main reinforcement that's bad.
And that creates this very narrow window.
A really narrow optimized processing window that you absolutely have to hit to unlock the peak performance. It's all about controlling that delicate molecular dance at the interface. Get it right, and the results are amazing. Get it wrong, and they plummet.
So summing up the amazing part then, we're looking at UHMWPE self-reinforced composites with, well, exceptional tensile strength, that 1440 MPa figure, capturing maybe up to half the strength of the original fibers.
Which is incredible efficiency.
Plus, they fail gracefully, right? Not brittle fracture, but that ductile bending and energy absorption. Fiber pullout, plastic deformation.
Yeah, really important for impact resistance and avoiding catastrophic failure. And we absolutely have to circle back to the sustainability angle.
The monomaterial aspect.
Right, because it's all basically polyethylene. Recycling becomes much, much simpler compared to traditional mixed composites. It fits beautifully with ideas like the circular economy.
So it's strong, it's tough, and it's potentially much more environmentally friendly.
That's the trifecta they're aiming for.
Okay, so here's something for you, our listeners, to think about. As you consider the kind of precise control needed here, this molecular level tuning, to create these high-performance, single-material composites. Think about this.
Where else could this apply? What other materials or systems out there might benefit from understanding a similar delicate dance between bonding and structure?
And maybe more broadly, how could this whole principle of monomaterial design start to shift how we approach engineering and manufacturing in general?
Could it lead to more sustainable, maybe more adaptable, certainly robust technologies across all sorts of industries? From everyday items maybe, right up to components for the most extreme environments imaginable.
Something to definitely ponder.